So we're ready to begin talking about applications of differentiation. We've basically gone over all the differentiation rules we want to know, probably more than we want to know, I would guess, but we're ready to really dig into how derivatives can help us solve problems. And so we're going to begin talking about types of problems called related rates problems. And this problem that I have written here, it's a word problem, is an example of a related rates problem. So I want you to read it. Take just a second. So like I said, this is called a related rates problem. Related rates. And a related rates problem is nice because the name of the problem actually tells you exactly what you're supposed to do to solve the problem. So we're really zooming in on the case where we have two quantities that are changing with time. So this time when we say rates of change of a quantity, we really mean the special case where the independent variable is time. So two quantities that are changing with time, and the goal is just to relate those rates of change. That's, in a nutshell, what a related rates problem is. You have two quantities that are changing with time. You want to relate their rates of change, or in other words, you want to relate their derivatives. So let's see the strategy for solving a related rates problem, like the one we have here. So I tried to boil it down into 3 steps. And now this is not a catch-all. There's always variations to this, sort of bullet point methodology of solving problems. And one of the reasons why this section is a little bit difficult is because it involves word problems. And it involves problems where maybe the wording of things can be confusing. It may not be exactly clear what the question is asking. Hopefully the question is written well so you can figure out what it's asking. But the idea is to do the following. So because this is a word problem, I would like to kind of extract the key information as quickly as possible. And one great way to do that, especially for a lot of learning styles, is to draw a picture. So instead of reading about what's happening in this picture, in this problem, if I can portray it as a picture, then it's going to help me just visualize what's going on. And also in that picture, I can label the relevant quantities. So the quantities that are changing with time. And I can also kind of state exactly what I know about those quantities and exactly what I'm looking for. So I'm sort of just taking the word problem and putting it in kind of schematic format in a picture, and then just bare bones what I know, what I want to know. The second step is to really key on the two quantities that you're trying to relate, or more specifically, the two quantities whose rates of change with time you're trying to relate. So this normally just involves writing down an equation that relates the variables. So maybe, in this example, it looks like we have volume and radius. So can I write down what the volume of a sphere is in terms of the radius? So maybe you just go look up on the internet, what's the volume of a sphere? 4/3 pi r cubed. That's your relationship between the relevant variables. And then the last step is to take the derivative. So you relate the variables, and then you use implicit differentiation to get a relationship between their rates of change. So that's how it goes. So let me walk you through this example that we have here about the spherical balloon and try to boil it down into doing these 3 steps. Okay, so here I've done step 1, or at least the first part of step 1. I've drawn a picture, and now this picture does not have to necessarily be a good picture, but like I said, for a lot of people, if you can visualize, okay, this is a sphere. It mentions the volume, so let me give a name. So I'm going to say that V is the volume, and this r is the radius, because I see those seem to be important to the problem, right? Because I want to know something about the volume and the radius. So what do I know? Okay, so a spherical balloon is blown up, and the radius of the balloon increases. So let's highlight this. Radius of the balloon increases at a constant rate. And here's the key word right here. When you see the word rate, you should immediately think rate of change or derivative. What this sentence is telling you is the rate of change or the derivative of the radius with respect to time. So here's what I know. I know dr dt equals 2 inches per second. Okay, so you see I'm just trying to pick out information about the rates of change of one of the two quantities I'm trying to relate. And now let's look over here. Here's the question. At what rate is the volume of the balloon increasing? Now, it's not telling me what the rate of increase of the volume is. It's asking me. So that means I want to know, again, the rate of the volume or the time derivative of the volume. So what I want to know is dv dt, so the time derivative or rate of change of v. And this last part says when the radius is 6 inches. So when r equals 6 inches. So this is kind of step one. And to the degree that you can do step one really well, will make steps 2 and 3 go really smoothly. Okay, so clearly identify the two things, the two variables that you're trying to relate, their rates of change. Then write down what you know. So typically you'll know the rate of change of one of them, and you'll want to know the rate of change of the other. Okay, and just thinking about this problem, it's kind of interesting. So you know that the radius of the balloon, you could just measure that, how it's increasing, and you want to know, well, how much air is getting put in? What's the volume changing as I blow into the balloon? So it's a pretty interesting concept. You know how something's changing, how is something else changing? Okay, and we'll see a lot of examples of this, and you'll start to see why derivatives are so helpful. Okay, so step 2 was to straight up relate the two quantities. So that was V and R. And this is where, I'm not saying you should know every formula for every volume or every situation you go into. So this might require a little bit of research, looking at what is the volume of a sphere. And maybe you know, maybe you don't, but I'm going to tell you, the volume of a sphere is 4/3 pi r cubed. But there's nothing really magical about this step because it's just information that I either know or I need to look up and figure out the relationship between V and R. Volume of a sphere is 4/3 pi r cubed. And that's all we do in step 2. Then in step 3, we use implicit differentiation to differentiate this equation, not with respect to R, not with respect to V, but with respect to the independent variable t. Okay? So what is the rate of change of V? Well, don't think too hard. It's just dv dt. Nothing special there. And then 4/3 pi, that's just a constant. And then I need to take the derivative of r cubed. Again, not with respect to r, but with respect to t. So we need to use the chain rule. this is going to be 3r squared, and then times dr dt. Okay, but now we're all set, right? Because we're looking for dv dt. And so here's what it equals. Well, okay, what's dr dt? I know dr dt. dr dt is right here, 2. And then what about r squared? Well, that's what this sentence is for right here, when the radius is 6 inches. So we don't just want to know dv dt at any time. We want to know dv dt specifically when r is 6 inches, because dv dt may not be constant. And in fact, it is changing here. It actually depends on the radius. So we want to just set r to be 6, dr dt to be 2, and let's see what happens. So dv dt in our case is equal to 4/3 pi times 3 times 6 squared times 2. Okay, and we multiply all this out, and what do we get? Well, this is basically, so the 3's will cancel, and we have 4 pi times 36 times 2, so 72 times 4, that's 288 pi. Okay, and the units are going to be important since this is a real physical application. So we're looking at a rate of change of volume with respect to time, so it should be inches cubed per second. So if the radius is increasing 2 inches every second, when the radius is 6 inches, that means the amount of air that's being blown into the balloon is 288 pi inches cubed per second. And that's how a typical related rates problem will go. All right, so here we have another typical related rates problem. So I'll give you a second to read it. Okay, so I've already done the beginning of step 1 for you. And that's I've drawn the picture. Okay, and I'll say that, when you're asked a related rates problem, it's really nice to be given the picture. Sometimes if you don't have the picture, it's really hard to see what's going on. And so hopefully this picture will help you kind of visualize the situation. So here's the pole right here. Pole, and here's our man right here. So the pole is 15 feet tall, the man is 6 feet tall, and of course the man is moving this way, away from the pole. Okay, walks away from the pole. And I just labeled, okay, this is a little bit of insight that I had. I labeled the distance from the man to the pole is x, okay? And then the distance from the man to the end of his shadow as y. Now this is not the only way to do it, and it might not be the best way to do it, but it doesn't really matter because as long as you do it some way that's correct, it's fine. So sometimes if you don't have a picture, if you're not sure, just label it the way that makes sense to you, and you might be right. But here's the way I labeled it, just so you can see an example, and this will work out. So let's go back to the problem and look for some keywords. Okay, so a street light is mounted at the top of a 15-foot pole. Well, that's just telling us that that's 15 feet. A man 6 feet tall, that's just telling us this, walks away from the pole with the, well, here's a keyword. Now, it doesn't explicitly use rate, but that's just the problem with language. We don't always use the same words. But speed is definitely a keyword that tells you there's a rate of change going on, especially with someone moving. You know they have a velocity. Velocity gives us a speed. This 5 feet per second is telling us a rate of change. Now, what is it telling us? So the man walks away from the pole with that speed. So that means if the distance away from the man and the pole is x, 5 is the rate of change of x, or in other words, dx dt. So we actually know dx dt is equal to 5 feet per second. Okay, so hopefully that makes sense. And again, I'm just writing down what I know. I have these quantities that I'm calling x and y. I know that the x is changing at a rate of 5 feet per second. Let's keep going. So we want to know how fast is the top of his shadow moving when he is 40 feet from the pole. Now, this question is a little bit tricky because when it says how fast is the top of his shadow moving, it's asking for a rate of change. And you might want to jump in and say, oh, okay, it's asking for dy dt. But notice that dy dt is the distance from the end of the shadow to the man. Or that's what y is. So in other words, dy dt is going to be the rate of change that the end of the shadow is moving away from the man. But if we just want to know how fast it's moving, we actually want to know how fast the end of the shadow is moving relative to the pole. So this is kind of a very simple velocity addition. So what we want to know is not quite dy dt. What we want to know is dx dt plus dy dt. And take a minute to make sure you understand that, because it is very subtle. Dx dt is how fast the man is moving relative to the stationary pole. Dy dt is how fast the end of the shadow is moving away from the man. If we want to know the velocity, or how far away the end of the shadow is moving relative to the stationary pole, or to a stationary observer, we need to add the two velocities. If you prefer, think about you're driving in a car and you throw a rock forward with a velocity. The velocity of the rock, or the speed of the rock, is not how fast you threw it. If I'm standing on the side of the road, I'm going to have to consider the fact that the rock is already moving at the speed of the car when you threw it. So the total speed of the rock is actually the sum of how fast I'm moving in the car and how fast I threw the rock. So that's why we have to add dx dt plus dy dt. And now we want to know dx dt plus dy dt when what? So that's the last part. When the man is 40 feet from the pole. So in other words, when x equals 40 feet. So that is the completion of step 1. We drew the picture, labeled the relevant quantities, stated what we know, stated what we want to know, exactly when we want to know it. Okay? So then, moving on, step 2 is to relate x and y. And one of the trickiest parts about related rates is that a lot of times it'll use facts from geometry, trigonometry, maybe even some physics facts that may be in your mind or they may not be. Now what we need to use here is something that I believe you've learned before, but there's a very good chance that it's probably not at the forefront of your mind right now. So in order to relate x and y, what we need to notice is that we're actually dealing with similar triangles here. See, was that the first thing you thought of? Probably not. So look at this big triangle right here. Okay, so this is the outer big triangle. And then we also have the inner triangle right here. And they are indeed similar, okay? And what do I mean by similar? I mean they have the same angles. And similar triangles have a very special property. They have the property that their side lengths are proportional. So that means this side right here, the 6 foot side, the same scaling that I need to do to get from 6 to 15, I need to do to get y up to this whole length, y plus x. So in other words, or maybe put a little bit more succinctly, 6 is to 15. So this side is to this side as, well, I go back to this triangle, y is to this whole length of the big triangle, which is x plus y. Okay, and again, that's just using similar triangles. All right, but this does give us a relationship between x and y. And I'm actually going to simplify this relationship a little bit. So I'm going to cross multiply. So that gives me 6 times x plus y. 6 times x plus y equals 15y. And this is 6x plus 6y. So if I subtract 6y, I actually get a very nice relationship. 6x is equal to 9y. Okay, so here's my relationship between x and y. So what's step 3? Step 3 is to use implicit differentiation to relate, not the variables, we've already related the variables, relate their rate of change. So we differentiate, we get 6 times dx dt equals 9 times dy dt, because when I just take the rate of change of x, I get dx dt, rate of change of y, I get dy dt. And now I know dx dt is 5, so this is 6 times 5 equals 9 times dy dt. Okay? Or in other words, dy dt is equal to, well, 6 times 5 is, let's see, 30. Okay, so looks like we have 30 over 9, and this will be feet per second. Same units as dx dt over here. But now remember, we're not looking for dy dt, we're actually looking for dx dt plus dy dt. So what is dx dt plus dy dt? Well, that's just 5 plus 30 over 9. And if you like adding fractions, I mean, who really does like adding fractions? But if you do, I believe this is 75 over 9. And the units are feet per second. And so, of course, that's just a little bit bigger than 8 feet per second. Okay, so this is another typical related rates problem. So you see where the challenges can be. First of all, visualizing the problem. Second of all, using whatever geometry facts you need to relate the variables. So all of these, math facts that you learned a long time ago may come back to haunt you. And then probably the easiest part is the calculus because you just differentiate and plug in. I mean, that's as easy as it gets. But again, we're seeing that calculus is not difficult in sort of its purest form. It's difficult because it draws on so many different classes that you've taken before you've taken calculus. Okay, so this is probably one of my favorite related rates problems. Because, I don't know, every time I see a ladder leaning against a wall, it reminds me of this problem, brings back some good memories of doing calculus. So, anyways, I'll give you a minute to read it. Okay, so it looks like we're trying to find the rate of change of the angle. Now notice I've already done you the great service of drawing the picture. So here's the ladder leaning here. And so the angle that I labeled here, okay, so the angle between the top of the ladder and the wall, that's right here, so I'm just calling that theta. And then, of course, the length of the ladder is 10, so that's not going to be changing. I mean, we're assuming some ladders actually will extend out, but let's assume that this is a rigid 10-foot ladder. And then the height above the ground where it meets the wall, we're calling y. And then the distance away from the wall horizontally is x. Okay. So what do we know and what are we looking for? Okay, so 10-foot wall ladder, bottom of the ladder slides away from the wall. Here's our keyword. At a speed of 2 feet per second. Okay, and that's away from the wall. So this is a rate of change of x. And the direction is really important here because it says the bottom of the ladder, which is right here, is sliding away from the wall. So what this is telling me is dx dt, the rate of change of the distance from the wall to the end of the ladder, is 2 feet per second. So of course, if this end of the ladder is sliding away from the wall, we assume that this end of the ladder is sliding down the wall, right? So hopefully you can visualize. And I mean, if you can't visualize it, go find a ladder, or maybe not a ladder, maybe a book, and lean it against the wall and just watch it slide. And I hope that, that's the nice thing about these very concrete examples. If you ever get lost, you can always just go do it and see what's happening. Okay, but the distance away from the wall is changing at a rate of 2 feet per second, dx dt. So that's what we know. And then next, what we want to know, how fast is the angle between the top of the ladder and the wall? Here's our keyword, changing. So I want to know the rate of change of the angle. Specifically when the angle is pi over 4 radians. So I want to know d theta dt when theta equals pi over 4. Okay, and that's what we called step 1. I'll probably stop labeling it step 1 because it really is more just a guideline of what to do. It kind of goes back to basic problem solving. When you have a word problem, what's the first step? You just want to extract all the relevant information. You don't want to have to reread the word problem 100 times. So here's all the relevant information. So now my goal is to relate the relevant quantities. Now I know dx dt, and I'm looking for d theta dt. So I need to relate x and theta. But notice that this is a right triangle. That's kind of the key observation. Now I guess if you're kind of a devil's advocate, you could argue, well, how do you know that the wall isn't leaning? Well, okay, we're gonna assume that the wall is straight up above the ground. Okay, so it really makes a right angle with the ground. Otherwise, we would have to do some measuring, I guess. Okay, so we can use trigonometry, is the point. So we want to relate theta and x. Now you see this side y. I could use y, but this is actually kind of a red herring. I really don't need to know anything about y. I really only need to know a relationship between theta and x. So what I'll do is I'll use sine, because sine of theta is opposite over hypotenuse. So x over 10. So sine theta equals x over 10. Okay? Looks good. So now, what's the next step? Differentiate. So if I just differentiate this relationship between x and theta with respect to t, what do I get? Cosine theta is the derivative of sine, but then I have a factor by the chain rule, d theta dt, equals, well, this is just like 1/10 x, so in other words, 1/10 times dx dt. Alrighty, great. So let's look here. We have dx dt, which we know, okay? That's going to be 2. So we'll plug in 2 there. So 1/10 times 2 equals d theta dt. Okay. And now, let's see. We need to know what cosine theta is. Well, we want d theta dt when theta is pi over 4. So in other words, we just want to use cosine of pi over 4. But what's cosine of pi over 4? It's 1 divided by square root of 2. Now some people will tell you that it's square root of 2 over 2, but that's actually the same thing, just rationalized. I prefer to think about cosine of pi over 4 as 1 over square root of 2. Okay, so then d theta dt is, okay, so 1/10 times 2 is 1/5, so it looks like it's going to be square root of 2 divided by 5. And now the units here are going to be radians, right, because that was the unit of angle, per second. Okay, and of course this has a numerical value that would probably mean something more to you, and probably even more so, you can convert it to degrees per second to see kind of how fast that angle is opening up as dx dt increases this way. And notice that the fact that the answer is positive is significant. If it were negative, that would mean the angle would be getting smaller. But that would not make sense for the end of the ladder down here sliding away. You can see that we should get a positive answer. As this, again, as this end goes out this way, this end is going down, and so this angle between the ladder and the wall should be increasing. And specifically, when theta is pi over 4, is increasing at this rate. Okay, so we have another problem here about a plane, and I'll give you a minute to read it. Okay, so we have this plane, and we have a radar station. So here's the radar station down here. And then hopefully you can tell this is a plane. Okay, and I drew the picture for you again and labeled it. Now we're told that the plane is flying at an altitude of 1 meter above the radar station. Okay. And then the horizontal distance from the radar station is labeled x. And then the distance, which this is what I mean by distance, from the radar station to the plane is labeled s. So what do we know? Well, let's look for our keywords. Planes flying horizontally, flying horizontally, here we go, at a speed of 500 miles per hour. So the horizontal speed, or the horizontal rate of change of the plane, is 500 miles per hour. So in other words, dx dt is 500 miles per hour. Alrighty. Now we want the rate of change at which the distance from the plane is increasing. And now here this distance means the distance from the radar station to the plane. So we want to know ds dt, the rate of change of the distance from the radar station to the plane, when s equals 2 miles. Right? Because when the distance, or when the plane is 2 miles away from the station. Okay, so there we go. Everything's all set up. Now it's just a matter of relating what we know and what we want to know. Now we know information about the rate of change of x, and we want to know information about the rate of change of s. So we need to relate x and s. Well, again, notice that this is a right triangle. This is the vertical distance. This is the horizontal distance. So those will be perpendicular. And then the actual bird's eye distance is the hypotenuse of this right triangle. So we can relate x and s by the Pythagorean theorem. X squared, so this side squared, plus this side squared, which is always just equal to 1, is equal to s squared. Alrighty, easy enough. Now what do we need to do? Well, we need to find the rates of change. So let's differentiate. Let's use implicit differentiation. So the rate of change, x squared, with respect to t, that's going to be 2x times dx dt plus, well, the derivative of 1 squared is 0. Another way to think about it is that the vertical distance is not changing, so it doesn't contribute to the rate of change. And that's equal to 2s times ds dt. Alrighty, so now we've related the rates of change. The only thing we don't know now is these two variables, x and s. Now that's not entirely true, right? We do know s. We know s is 2 miles. We want ds dt specifically when s is 2 miles. But what about x? What is x when s is equal to 2 miles? Well, this is when we go back and use our relationship between x and s. If we need to know x when s is 2 miles, let's just do it. So when s is 2, s squared is 4. Or in other words, x is equal to, so if we subtract, we'll get 3, take the square root. Of course, we want the positive square root because this is an actual distance. It wouldn't even make sense to talk about a negative distance in this context. So when s is 2 miles, x is the square root of 3 miles. And so over here we have 2 times x, which is square root of 3, and then plus 0, equals 2 times s, so 2 times 2, And then ds dt is what we're looking for. And I forgot something important. Forgot dx dt. We also know what dx dt is. So dx dt is 500. And that equals 2 times s, which is 2, for ds dt. Okay, so then we'll just divide by 4. So one factor of 2 from the 4 cancels here. The other one can make this 500 divided by 2, which is 250. So it looks like ds dt is going to be 250 times the square root of 3. And just in case you want to know, this is approximately 433 miles per hour. And now it's kind of nice to think about whether that makes sense. Okay, so if the plane is flying horizontally at 500 miles per hour, we would expect the distance to be increasing slightly less, at a rate slightly less than 500 miles per hour. Because not all of this 500 miles per hour is changing in the direction away from the radar station. It's actually in a direction kind of along the horizontal, whereas there's this distance of 1 mile in the vertical direction. So this makes sense. Okay, so now that we're getting the hang of these related rates problems, let's try one that would be considered difficult, maybe. Okay, but let's just take our time and think it through. So I'll give you a minute to read the question. Alrighty, so I did the service of going ahead and drawing the picture. We have the water in the tank, radius r, and the height is h at any given time. Those quantities are changing. And of course the volume is also changing. But the dimensions of the cone are fixed. So the height of the cone is 6, and the diameter across the top of the cone is 4. Okay, so let's see what we know and what we're looking for. So water is leaking out of a conical cone at a rate, so here's our keyword, of 10,000 centimeters cubed. So you might be tempted to say, okay, well that's dV dt. But wait, there's a little bit more. At the same time, water is being pumped into the tank at a constant rate. Okay, so this is a little bit confusing. The tank has a height of 6 meters, and okay. Then what else do we know? The water level is rising at a rate of 20 centimeters per minute. Okay, and then we want to know the rate at which water is being pumped into the tank. Okay, so it looks like to me that we know dH dt. That was pretty clear. The water level is rising at a rate of 20 centimeters per minute. So that's saying dH dt is 20 centimeters per minute. That's what we know. What do we want to know? Well, we actually want to know the rate at which water is being pumped into the tank. But notice that water is also leaking out of the tank. So what we have is that the rate of change of V, dV dt, is going to be, well, the rate at which water is being pumped in, which we don't know. So let's just make a note that this is rate of water in, plus, actually not plus, minus the rate at which water is leaking, which is 10,000. Okay, so why is that? Because if I just think about the net change of water, if water is falling out of the cone and water is being pumped into the cone, the total change in the volume is the difference in the volume leaving the cone and the volume being pumped in. So it's the rate of water in minus the rate of water out, which we know is 10,000. And what we want to know is this R right here. Want to know. Okay, so we don't want to know exactly dV dt, but we basically want to know dV dt plus 10,000, right? So if we know dV dt, we just add 10,000, and we have R, the rate at which water is being pumped in. Okay, so hopefully you followed all that. There is one more thing that we should note, and that's we know the water level is rising at this rate when the height is 2 meters. So actually we want to know R when h equals 2 meters. Okay, and I believe that's everything out of the problem that we've extracted. We've drawn the picture. We've said exactly what we know, what we want to know. Looks like we're ready to try and relate the variables we're interested in. So since we know the rate of change of the height, dh dt, and we're looking for basically dV dt, that's going to be step 1, let's relate h and v. Okay, so we need the volume of a cone. Well, if you don't remember, the volume of a cone is 1/3 the area of the base, so that's pi r squared, so down here, pi r squared, times the height. Okay, that's the volume of a cone. But notice that this relationship relates v, r, and h. We only want a relationship between v and h. So what's going on here? Well, this is again where we're going to have to use a little bit of geometry. So if you look at this picture, and I draw a line straight up through the middle, and over, we have a triangle, actually a right triangle. And then if I look right here, I have another triangle. And you can probably guess that these two triangles are similar. So actually R is determined by H and H is determined by R because of the dimensions of the cone. Whatever H is, I can figure out what R is because I'm living in a conical reservoir. And so it looks like we have R is to, well, this is the diameter, so that 4 is the diameter, so the radius up here is going to be 2, half the diameter. So it looks like R is to 2 as H is to 6. Or in other words, R is equal to H over 3. So now we can just plug in H over 3 for R squared. So that's going to give us h squared divided by 9. But we're also multiplying by 1/3, so I think all in all, we're going to get pi times h cubed over 27. Okay, and again, that's coming from just plugging in r equals h over 3. So we're going to have h squared over 9. So h squared times h gives me the h cubed. And then the 1/3 times 1/9 gives me 27. And the pi is just hanging out. All right, excellent. So let's differentiate. What is dv dt? Well, this is a constant, so I'll just bring down the 3 when I differentiate h cubed. So it looks like I'll have pi over 9 times h squared. And then we tack on our chain rule factor of dh dt. Okay, everything is looking great. Now we want to plug in what we know. But there's something else very tricky about this problem that you would probably overlook. Notice that dh dt is 20 centimeters per minute. But we're given that the height at that time is 2 meters. We have inconsistent units. So we better make sure that our units are the same. So here's what I'm going to do. I'm just going to simply write that h is not 2 meters. Well, how many centimeters are in a meter? There's 100. So h is actually 100 centimeters. And so I'm going to work the rest of the problem in centimeters. Okay, so everything should be okay now. So we have dv dt is equal to pi over 9 times 200 squared times dh dt, which is 20. Okay, everything looks good. And this is our final answer. Now, that's the final answer for dv dt. So what we're actually looking for is this factor r, which is the rate of water in. And so to get r, we just need to add 10,000 to dv dt. So that's pi over 9 times 200 squared times 20 plus 10,000. And the units are going to be centimeters cubed per minute. And it's centimeters cubed because it's a rate of change of volume and per minute. So here is our final answer. Hopefully that wasn't too bad. But you can see that in these related rates problems, there are a lot of different curveballs that can be thrown. Now I think that kind of doing unit conversions and stuff is maybe outside the scope of a calculus class, but it's something to think about. Certainly in the real world, you need to deal with units and you need to make sure that units are consistent. So it is a good thing to think about.